All right, let's talk about optimization. So I was going through some of the questions that we've looked at, and essentially, I think there's a bunch of questions like in particular that you can look at. So maybe I'll make this video about just maybe one problem and general strategies for optimization. So what's really happening in optimization problem? Optimization problem, it's actually the closest to a real life situation, right? Not only because it's talking about something useful, like, usually we want to maximize or minimize something, but also because of the way these problems work is you have to figure out the question by yourself, right? So what is this optimization really doing? What is happening is it's kind of like, how chemistry and physics and biology have their labs and people go and work on these labs, and um, they measure things and then they make hypotheses, they test them, and so on. So but what does a mathematician do? The mathematician doesn't go anywhere. They just sit in the room with pen and paper. That's the lab. So essentially, an optimization problem is like a lab. It's like you're given an experiment to perform, right? And the experiment has a bunch of knobs to control. Like, you gotta spin them, they've got certain settings, and when you spin these knobs, there's some output here which fluctuates, like oscilloscope used by physics people, or like chemical reactions or biology, whatever they do. And then you're asked two questions. You're asked what setting of the dial will maximize this and what setting of the dial will minimize this. However, the problem here is that in the math optimization scenario, you also have to figure out the dials. Okay, so basically you have to set up the experiment so that you have these dials. Now these dials are basically your variables. So once you figure out these variables, you can figure out the min and the max. But we run into some problem here. Run into problem in the sense that with our current tools, right, we say we can only have one true dial, right? Meaning that even if we have these multiple dial, there's one that is the major one, which means that when you turn this, these kind of automatically adjust the remaining dials. So it's basically, that's because right now we are working or learning calculus of one variable. When you know calculus of multivariable, then it becomes a more complicated situation and more closer to real life. Because in real life, you actually have a lot of parameters that you have to worry about, and you may never find a solution, right? You just find somewhat best solution. So one variable case is neat in that sense that you can actually find solutions that are like exactly the solutions, right? So what's going to happen is there's going to be a bunch of variables, but there's going to be one which we can call the primary variable, and these depend on the primary, right? So when you're looking at the optimization problem, right, the first thing maybe is to figure out the variables and pick one as primary. Okay, so that's like basically defining the dials. Then you got to figure out how the other variables, how many soever they are, depend on the primary variable. So that cannot be random, right? It's like, so we're basically saying that we need to know how changing this primary knob changes the other knobs. Okay, so some sort of relation that we have. And then lastly, we need to know what is being optimized. Okay, so what is this? What is being optimized will be depending on all of the dials. And then what you do is you kind of plug in these into the optimization, and then you land up with a max-min problem. Yeah, then you use calculus. So I think that the most troublesome step is these first three, because these first three have nothing to do with calculus. They have to do with changing English into math and using a bunch of random things that you've learned before. Like it could be arithmetic, it could be geometry, it could be trigonometry, right? So it could be something about the coordinate system. So it can be any old thing. So step 1 to 3, that's why it's always confusing, because it's not really calculus. It's not what you've learned in this course. However, all these skills are complementary. So, without the skill to know without knowing some basic geometry, calculus is just a tool, so it won't be very useful, right? So it's kind of like saying you can have, say you're doing some woodworking and you have all these fancy equipments, but if you don't know the basics of like which direction should you be sanding, or if you're cutting, should it be with the grain against the grain, it's not gonna work out. You can't just have the equipment. So you can't just have all perfect knowledge of calculus. You also need to have some knowledge before, so you can do these steps 1, 2, and 3. So looking at the questions, I don't know which one to pick. So we've done a bunch of questions. Okay, let's do one that I have not discussed in class. So this is worksheet 12, number 4. There are two poles which are some distance apart. So, doesn't say they are same height, so let's assume they are not. They are secured by a rope that goes from the top of one pole to some point on the ground, and then from the ground to these other one. Let the angle on the ground made by the rope be theta 1 and theta 2, rope on the ground. So that's theta 1 and that's theta 2, where these angles are facing one of each of the poles. Okay, so that's correct. I label the right angle, like right in the sense of it being correct. Show that for the length of the rope to be minimum, the optimum condition is theta 1 equals theta 2. How does this relate to a law of reflection of light? So related to what we did in class. So what is it trying to do? It says minimize length of rope. Right. So what is varying here? The poles are fixed. Right. So the poles are fixed. I'm just going to call this H1, H2. Now what is varying? Let's draw some pictures and I'll know what is varying. I can choose this point to be here, and I can get a completely different structure. I can choose this point to be here and I can get completely owl structure. So it's this that is varying. The position of this point varies. Another thing that is fixed is the distance between the poles. Let's say the distance between the poles is some fixed distance, d. Okay. So again, that might be another annoying part, is that you have to come up with some of the constant names too sometimes, if they are not given to you as numbers. So now I have this some point here. I have this whole thing is d constant, h2 constant, h1 constant. Now the position varies. So let's say I call this position x, and this would be d minus x. This is theta 1, this is theta 2. Now what am I trying to minimize? I'm trying to minimize this length. Right. Now I can use Pythagoras theorem, right? Find the length as h1 squared, h1 plus x, h1 squared plus x squared, square root, and so on and so forth. However, let's go back to the problem. What are we trying to show? The condition we are trying to show is not on x. Yeah, we're not trying to find how far it is. We're trying to show something about the angles. So we're not going to use Pythagoras theorem. We're going to work with the angles in that case. Okay, so what does that mean? That means we need to find this length in terms of the angles. Now, the moment you hear angles and lengths, what relates them is trigonometry. That's the whole field of angles and lengths. So let's see. AB, so if I take sine, right? Sine of theta 1 is opposite over hypotenuse. So this length comes out to h1 over sine theta 1. Similarly, sine theta 2 would be h2 over bc. So bc would be h2 over sine theta 2. h1, h2 never mind because they are constant, so that's fine. But this theta 1, theta 2, so the length is now h1 over sine theta 1 plus h2 over sine theta 2. Now the problem here is, a solvable problem is that there's two variables involved. Right? So which means we need to do this figuring out how one variable is associated with the other variable thing. So when we look at finding relation between theta 1 and theta 2 here, there isn't much relating theta 1 and theta 2, right? So we have to be a little creative here because we don't know what this angle is going to be for sure. It's going to vary as well. So maybe it will make more sense to revert back into the x situation here. That's what I'm currently thinking. If something else comes in mind, I will add another solution. So I'm going to go back into using x's here. Okay, so instead what I'm going to say is I'm going to say AP is square root of x squared plus h1 squared, and BC is square root of h2 squared plus d minus x squared. Right, so the length is square root of x squared plus h1 squared plus square root of h2 squared plus d minus x squared. Now I take the derivative because of the square root thing. This is a square root. This becomes a 2x. Again, square root of the whole same thing. This becomes 2 times d minus x, but with a negative 1. Right, so let's cancel the 2's and the 2's. Set this equal to 0. So I get x h2 squared plus t minus x squared minus t minus x square root x squared plus h1 squared equals 0. So what do I do now? Yeah, it doesn't look really good. Let's move them to opposite sides and square. So I have x squared h2 squared plus d minus x squared equals d minus x squared plus h1 squared. Foiling out, I have x squared h2 squared plus x squared d minus x squared is x squared d minus x squared. Good news here, d minus x squared h1 squared. So these are same, they cancel out. What we have now, x squared h2 squared minus d minus x squared h1 squared equals 0. So what is this? This is h2x whole squared minus d minus x h1 whole squared equals 0. So we can apply difference of squares, h2x minus d minus x h1, h2x plus d minus x h1 equals 0. Okay, so I have h2x minus dh1 plus dh1x equals 0, or h2 plus dh1x equals dh1, or x equals dh1 over h2 plus dh1. Or I have h2x plus dh1 minus h1x equals 0, which gives me dh1 equals h1x minus h2x, gives me x is dh1 over h1 minus h2. Now this over here, it depends on h1 minus h2, which could be negative, right? Because it doesn't really say. The problem is for any two poles. It doesn't say, which pole is taller or shorter, which means that this can possibly give me x negative, which doesn't make sense because x is a length in our diagram. So let's pick that to be x. So if x is that, then d minus x would be d minus dh1 over h2 plus dh1, h2 plus dh1, dh2 plus d squared h1 minus dh1. Okay. That doesn't look very nice. Okay, anyways, so let's see here. I'll go back to our diagram, yeah. Theta 1, theta 2. X, d minus x, h2, h1. Right, yeah. dh1 over h2 plus dh1 and dh1 over h1 minus h2. Maybe we have to check which of these is minimum. Okay, let's keep this. So here, let's find what is tan theta 1. Tan theta 1 is h1 over x. So what we have for x is going to be h1 over dh1, h2 plus dh1 cancels, and it's actually h2 plus dh1 over d. And tan theta 2 is going to be h2 over d minus x. Which is going to be what? That's going to be h2 divided by dh2 plus, or taking d common, h2 plus dh1 minus h1 times h2 plus dh1. And these do not look the same to me. Okay, I found an error in my calculation here. Right here, this is x times h1, and I don't know why I put an extra d there. Right, so this is h1 plus h2. That looks much nicer. then d minus this guy is not going to have all this square crap. It's going to be dh2 plus dh1 minus dh1 over h1 plus h2, much nicer looking. Okay, sorry, let me get rid of all of this. Well, I mean, optimization problems always, you'll have to do sometimes maybe it works, maybe it doesn't. Careful about calculation errors. I always make a lot of calculation errors when I'm doing math. h1 over x, so h1 over dh1 times h1 plus h2. So this is h1 plus h2 over d, and h2 over d minus x is h2 over dh2 h1 plus h2, which is also h1 plus h2 over d, right? So what is that telling us? Oops. That tells us that tan theta 1 equals tan theta 2, and they are both acute angles, so theta 1 equals theta 2 as required. So that works out fine. So it kind of works like the light reflection thing, right? It's basically saying that if you want to find the rope with the minimum length, think what light would do. If you were light and you had to go from here to here after reflection, what you would do is you would choose to reflect at a point where these two angles are equal. These two angles being equal make these angles being equal, because then these are just 90 degrees minus, right? This is incidence, reflection, this is 90 minus I, and this is 90 minus R. So if I equals R, then 90 minus I equals 90 minus R, which is kind of neat because we're basically using nature's minimization technique to minimize like something in construction for us. Okay, well actually, now that I think of it, since it's kind of like light, we can even do this the way that we did for the light. Then we can use that trick where you reflect this one down here and you connect and you use similar triangle. Yeah, that should also work. What was that? Let's see, we did that, yeah, right here. Yep. So you could also take, where is it, the reflection thing. Yeah, it's kind of the similar situation, except no poles here, we just have the height A, right? So yeah, I mean, sometimes the calculation is going to not look nice, so you'll have to take a look at it. And yeah, in any case, if you have any questions that come up during the exam, you just email me and I can sort of guide you in the right direction. Just don't wait till like 10 p.m. on Sunday to email. I probably will be up, but that's too close to the deadline. Ideally, so the reason I'm going to make it available tomorrow evening is so you can already take a look at it, even if you're not solving it, and kind of mark out like, hey, question 5 and 7 looks like I might have questions, so let me start with those problems on Saturday so I can ask a question. Okay, that's it for review. That's the last one. Yeah, hopefully it's helpful. We'll find out, talk on Tuesday, see if it was any useful. Thank you.